Hello, everybody, and welcome to online lecture number 1 for advanced hydrogeology. Today, we're going to be doing a little bit of groundwater flow and groundwater refresher. So I'm going to start off here and share my screen with you. Maybe. Okay, figured it out. All right, so today we're gonna try and remind ourselves about groundwater flow and porous media. And so I want to start off by just reminding ourselves or rethinking about a drawing of a representative elementary volume of porous media. And remember, the representative elementary volume is this sort of magical cube of porous media where we've got rock grains sitting in our cube. And in between these rock grains, we've got pore space. So I'm going to encourage you guys to get your notepads, go down to the bookstore, get a notebook, and take these notes along with me in these little lectures. And I'm doing that because actually the act of drawing porous media forces you to visualize it in your mind and to conceptualize it. And I think there's a lot of power in the act of writing and drawing in forcing you to think about what's going on and to remain engaged in the lecture. And the nice thing about the recorded video now is that you can go back or pause it if you need more time to draw. All right, so we've got this REV, which is a representative elementary volume of porous media here. And remember, the REV is it's like this magical scale where we get these emergent properties of the porous media, where things like where properties of the porous media emerge and achieve some average value that can then be smoothly varied through space. And we're going to give our elementary volume dimensions delta x, delta y, and delta z. The actual size of these REVs is, up for debate a little bit, or depends upon our system. But in general, is many hundreds of pore volumes. And so it's 100 to 1,000 times the grain size. So it's on the order of 10 centimeters for most porous media. All right, so let's talk about or recall some of the properties of our porous media. Well, remember that we're going to consider a porous media that has, we've got grains. So these are our rock grains. Or sediment. And then we have pore space. And that's just the space in between the grains. And we're going to consider porous media here that is got a mixture of water so some of our pore space is full of water, and some of our pore space, this is water, and some of our pore space is full of air. Okay, so some things that we characterize our pore space with. Well, I might want to know something about the volume of the pore space versus the volume of the rock, right? So our first property that I want you to recall is porosity. And I'm going to use N for porosity here. And porosity is the defined as the volume of void space divided by the total volume for, so this is the volume of pore space over the volume of the REV. All right, and it is, let's talk about the units. So porosity has units of length cubed over length cubed, so it's unitless. All right, and we can determine our volume of pore space, or the volume of pore space, by rearranging this. And so the volume of our pore space is equal to the porosity times the volume of the porous media. All right, so porosity. Okay, so the next thing we might be interested in is the volume of water in our REV. So if we go back up here and look at our REV, we've got a volume here that's full of air, and we've got a volume full of pore space. All right, so another characteristic we might be interested in is how do we characterize or quantify the volume of water in that porous media? Well, let's first define the saturation ratio. All right, and the saturation ratio R is the volume of water divided by the volume of voids. Okay, so what's the maximum value that saturation ratio can achieve? Well, the total space available in the porous media to hold water is essentially the pore space. So when all the pore space is full of water, all right, then my volume of water will be equal to my volume of voids. And so the max is equal to 1. All right, what's the minimum saturation ratio? Well, I could have perfectly dry porous media. I'd have a volume of water of 0, in which case my minimum is equal to 0. All right, so the saturation ratio is some ratio that essentially is the total volume of the voids that is taken up by water. It's a ratio, and it varies between 1 and 0. Another measurement we might use is the volumetric water content. And this ratio, volumetric water content, is defined as the volume of water, all right? But now it's normalized by the total volume of the REV, all right? We can sort of break this apart and play a little trick here and say this is equal to the volume of water divided by the volume of voids times the volume of voids over the volume total, right? And now I've just, all I've done is multiply by the volume of voids over the volume of voids. It's just a little trick. But now we can say this is equal to this guy over here, the volume of the water over the volume of the voids. Well, that's our saturation. And then the volume of the voids over the volume total is porosity. All right. So what is our max theta sub water? Well, we can have all available pore space full of water. If that's the case, then our volume of water will be equal to our volume of void space, and we will end up with the volume of the voids over the volume total. That's equal to 1. All right. And minimum, again, well, our volume of water can be equal to 0, in which case our volumetric water content will be equal to 0. Sorry, this is not 1, this is N, porosity. The maximum volumetric water content is porosity. Okay, so we've got some we can now solve these equations here for volume of water. All right, and we can say that the volume of water is equal to R times N times the volume total. And all I've done is set this equal to this and solve for VW. All right, and we end up with this relationship that relates the volume of the water to the volume of the REV using the saturation and the porosity. That's our okay. So we might be interested in not just the volume of the water, but the mass of the water in the REV. Well, let's start off by remembering the definition of density. All right, that is mass of water divided by the volume of water, right? So if I combine this guy and this guy, so we'll call this guy star. If we combine star and I, we can solve for the mass of the water as rho water R times N times V sub T. All right. Okay, so let's think about some units here. This guy, unit, well, that's unit of volume. This is unitless, this is unitless. That's unit of volume, so this is length cubed. This one here, volume over volume, that's unitless. All right, and this equation, the unit is unitless, unitless, mass over volume times volume. So lucky for us, the unit here is kilograms or mass. Okay. So these relationships allow us to think about how much water, how much air in terms of volume, how much water, how much air in terms of mass, all right? And then how do we relate the volume of water in our cube to the total volume of the cube? All right, so some calisthenics to think about how space is partitioned within our porous media. All right, now let's talk about fluid potential. So in our porous media, we have fluids of any phase, but let's focus in on the water. We have water, and we're interested in understanding what the total driving force is of the water. All right, and that driving force, it turns out, can be described with a property called fluid potential. All right, and fluid potential is, in general terms, it's the total energy per unit volume for the fluid. All right, and one of our general rules in life is that things go from high energy to low energy. All right, and so water moves from areas of high energy to low energy, and we're going to characterize that total amount of energy in the water by this value that we call fluid potential. All right, so let's think about, let's just do some unit analysis. So the unit of energy is a joule. All right. And if we recall, 1 joule is the energy required to move 1 kilogram, or sorry, to accelerate 1 kilogram, 1 meter per second squared over 1 meter. All right, and that is equal to kilogram, this is an M, meters squared per second squared. All right, so a joule so 1 joule per unit volume, all right, is equal to kilogram meter squared per second squared times 1 over meter cubed. That is equal to a kilogram second squared meter. Kilogram second squared meter. This is the unit of joules per unit volume. All right, so we're just going to kind of remember that here. So let's look at some of our potential types of fluid energy, and let's start off with pressure. All right, I think we can all agree that pressure is something that drives fluid flow. All right, and we're going to do something here that's important. We're going to assume a constant density. All right, so we're going to assume an incompressible fluid for now. Okay, so my pressure, if I have an incompressible fluid, is defined by this equation, rho g psi, where this guy psi is the height of water above a point. All right, so psi is the height of the water column above our point where we're interested in measuring the pressure. And the pressure then is given by rho g psi. Well, let's just do our unit analysis here. And we see that this is equal to density is mass per unit volume, meters cubed. Gravity is acceleration, so meters per second squared. And this guy is meters. Okay, we've got these two cancel, that cancels, and we get kilograms per meter second squared. And if we go up here, we can see that that is the unit of joules per unit volume. All right, so pressure is essentially equal to the pressure energy. This is the energy, pressure energy per unit volume. All right. Some other types of energy that we're going to be, that can drive fluid flow. Well, a real important one is gravitational potential energy. So water flows downhill. Payday is on Friday. Right? Well, water flows downhill because the gravitational potential energy is higher uphill than downhill. All right, well, gravitational potential energy is given by rho g z, where z is the elevation. Of our water above a datum. All right. This has the exact same units as density. I'm sorry, as pressure. It's density, acceleration of gravity times a height. All right. And so we're going to get the exact same units. And we can think of this as the gravitational potential energy in joules per unit volume. So this guy is PE is joules of gravitational potential energy per unit volume. All right, finally, we can think about the kinetic energy. All right, and KE is equal to 1/2 m rho squared. I'm sorry, V squared. mv squared, where this is the fluid velocity. All right. So fluid velocity, let's look at the units here of KE, 1/2, no units, kilograms. Oh, I'm sorry. It's mv squared for a mass. For a fluid, it is rho v squared. So let me erase this. Should be rho v squared. So we should have kilograms per meter cubed times meters squared over seconds squared. That's velocity squared. And we're going to end up with kilograms per meter second squared. All right. And again, this is joules per unit volume. So this is the amount of kinetic energy per unit volume. Of water. All right, so our total potential or our total energy, we can write then as phi is equal to pressure plus PE plus KE, all right? And we can expand this now to be rho G psi plus rho G Z plus 1/2 rho V squared. All right, and this is our total energy per unit volume. All right, so if we're in a slow moving fluid, so if V is small, then this guy goes to 0. All right, and so for most groundwater applications, the fluid velocity is pretty small and the kinetic energy loss or the kinetic energy is not a great source of fluid potential. And so we generally ignore it. All right, in which case we can write our total fluid potential now as rho G psi plus Z. All right. And now finally, we can divide our potential by rho G. That is equal to our total head, which is equal to the height of water above our point plus the height of our point above a datum. All right. This is the total energy per unit volume of water. Well, it's no longer per unit volume of water because it's been divided by density, but it's the total energy in our water. And it's given solely by a length. And that length is determined by the height of the water above our point and the height of the water below our point. And we call this the total head. This one is the pressure head. And this one is the elevation head. And the most important thing is that this head now For a constant density fluid, all right, this head is our a measurement of the total amount of energy in our water, and that our water will move from high energy to low energy. All right. And so it moves from areas of high total head to areas of low total head. Okay, so we've talked about how we measure the volume of water, the mass of water, and the energy of water in our porous media. Now let's talk about how we measure the flux or the flow of water through our porous media. All right, and the first thing we're going to talk about is the discharge. All right, and discharge is defined as the volume of water per time crossing a plane. All right, so it's the total volume of water per unit time crossing a plane. Um, we can think about this in another way, and that is discharge is equal to the fluid velocity normal to a plane times the area across which flow is occurring. All right, so this is the fluid velocity, and we're gonna our fluid velocity needs to be perpendicular to our plane. So it's all we care about is the fluid velocity normal to the plane. And so we're gonna take the dot product of the fluid velocity with a vector normal to the plane. This little n here is a special vector that is, if we have a plane, let's draw ourselves a plane across which we might be interested in the fluid discharge. And let's say that we have a fluid velocity vector v, all right? And it's coming in with some random orientation. N is the vector that is normal to this plane. That means it is perpendicular to this plane. By taking this dot product, all we're doing is making sure that we're getting the component of the velocity that's across the plane. So the velocity can kind of be oriented in any direction. And when we take the normal, we're just getting this component that is normal to our plane. We'll call that v sub n. It's the component of the velocity normal to our plane. All right, so this velocity is our fluid velocity vector. This is our normal vector. And this is the area of the plane. So this guy has some area A dot. Okay. So takeaways here, discharge is volume per unit time. That is also defined as the fluid velocity normal to our plane. All right, the component of the fluid velocity normal to our plane times the area of that plane. All right, and let's look at units here. This is length cubed per time. Velocity has the unit length per time. Area has the unit length squared per time. So again, we end up with length cubed per time. All right, that's good. Okay, so the problem here is that we always have to know this area of the plane for discharge. And that might be something that's intuitive, like in a river channel, but in groundwater flow, it doesn't make a lot of sense to always be thinking of discharge. Instead, we're going to use another unit, and that is the flux, little q. And we're going to define little q as the total discharge per unit area. All right. And this area is the area of the representative elementary volume. All right. So let's think about this, what this means. And let's draw another plane here. And this plane's in a porous media. So I'm going to put rock grains in here. Okay. This guy's got some unit, delta y times delta x. All right, so our discharge, and we've got some, let's give ourselves some fluid velocity flux. Randomly oriented V here, and we are interested in flow that is normal to our plane. So that's we'll have our normal vector here going out in 3 space. And all right. So our flux here is the total discharge measured across this plane. So this plane, let's give it a REV, has an area of delta x and delta y times delta y, right? That's the area of this plane. All right, so the flux here is all the discharge coming across this plane divided by the area of this plane. All right. Let's look at the units. So the Q is equal to big Q over A, which is equal to length cubed over time times 1 over length squared. This guy and this guy cancel, and we get length over time. All right, so discharge has the unit length over time, but it is not a velocity. All right, and the reason why is that our discharge Q is equal to the velocity dotted into the normal vector, but the area across which flow can occur is the area of the voids, right? It doesn't, no flow is occurring through the grains. So this is the area of the voids, right? And the area of the voids does not equal the total area of the plane. Right? And so if we want to know the relationship between the discharge and the velocity, we can substitute this equation into this equation, and we get little q is equal to v I'm just going to go ahead and take care of that dot product by putting this n here. That just means that I'm only interested in the velocity across the plane. All right, Vn times AV over A REV. All right, I just took this definition for Q, put it in here, and I divided by the total REV for the definition of flux. All right, and this guy, area of the voids divided by the total area, well, that's porosity. So we get discharge flux. So Darcy flux is equal to the velocity normal times porosity. Where the velocity normal is taken care of by the dot product of the velocity and the normal to the plane. If you haven't taken vector calculus and the dot product doesn't make sense to you, don't worry about it. All it ends up doing is making sure that we're getting the component of the velocity that's perpendicular to the plane. Okay, so now we have discharge, flux, and fluid velocity and the relationship between those three. Okay, now we're going to relate fluid flux and potential. And to do that, we're going to use Darcy's law. All right, and Darcy law relates flux and potential. And recall that its form is this, Q. I'm going to consider it one direction right now. Q sub x is equal to negative K dH dx. All right. And this term over here is the gradient in the head in the x direction. This guy here is the hydraulic conductivity that we're going to talk about. And this is our Darcy flux in the x direction, or the discharge per unit area. All right, let's deal with this, this negative sign. And let's draw ourselves another plane here. Okay, and we are interested in the flux between a point over here and a point over here on our plane. And at this one, we have a head. Let's just say that we have a head of 10. And at this point, let's just say that we have a head of 9. And this distance in between them in the x direction, we're going to say is 10. All right, so let's figure out why we need a gradient sign or a negative sign here. Well, here, delta H over delta X, this is equal to H1 minus H2 over X1 minus X2. All right, and so H1 would be 10. H2 would be 9. I'm sorry, I messed this up. The gradient, come on. The gradient, by definition, is H1 minus H2 over X1 minus X2. And our X is increasing in this direction, so we're going to give this an X of 0 and this an X of 10. All right, so this would be 10 minus 9 over 0 minus 10. All right, and so our gradient here would be negative 1 over 10. All right, so now I have Q is equal to negative K times negative 1 over 10. Now, we know that fluid flows from high head to low head. So here we have a head of 10, here we have a head of 9. We definitely want our fluid, it's definitely going to flow in this direction, all right? And that is the positive X direction. So we want, or we have to have Q sub X has to be positive, all right? Well, the only way for that to occur is to have this negative sign here. So negative 1/10 times negative K will give us a positive QX, all right? So we have to have this negative just because of this definition for gradient, all right? That's why that negative is there. Okay, so Darcy's law relates fluid potential and flux in groundwater systems, all right? And it just says that the flux is linearly related to the gradient, and the relation here is this hydraulic conductivity K. K is hydraulic conductivity, and that's the ease of water flow. All right, how well does water flow through our porous media? K is given by this, rho relationship. Rho G over mu. This is the water density, gravity, and this is water viscosity. And this guy here is the intrinsic permeability. All right, so this intrinsic permeability is we're going to call it the permeability in class, and it's the ease of any fluid flow. All right, and it's independent of these parameters here for water. So it's independent of density and viscosity. All right, so another way to write Darcy's then is Q is equal to negative K rho water G over mu times dH dx. And in this flux, we are explicitly pulling out the properties of the rock, which is the intrinsic permeability, and the properties of the fluid, which is water here. All right, intrinsic permeability has units of meter squared or length squared. All right. Now, we can relate any discharge and flux with our relationship that Q, big Q, is equal to little q times A. All right. And so another form of Darcy's is Q is equal to negative A K dH dx or negative A K rho G over mu dH dx. All right. So finally, let's talk about storage. And storage is some relationship between a change in head and remember head is a measurement of energy, right? So it's a relationship between the change in head or energy and the amount of water or volume of water in our REV. All right, so when we add more water or take more water away, we're going to change the amount of energy that water has. And storage essentially is that relationship. So let's define a few things. The first thing we're going to do is store activity. All right, and it's going to get a capital S. And storativity is defined as the volume of water over the volume drained or head drop. So the volume of head drop. Let's talk about what this means. And we'll do it with a little drawing here. So consider some column of aquifer. All right. Got our little column of aquifer. And if we were to put a well in this aquifer, so let's do that. Put a well into our aquifer. And we might find that the water level or the head in the aquifer is some height h naught above the top of our column here, all right? And then let's put a magical little spigot here. All right, and we drain some water out. All right, we drain some water out and we drop the head some amount down to H1. All right, so we've dropped the head by some amount and we got out some volume of water. All right, my volume of head drop is, so VHD is equal to the area here of my aquifer times the change in head of H naught minus H1. All right, this is equal to VHD. All right, it's like this kind of fictitious thing of just what is the volume of my aquifer that experienced a head drop. And all storativity is the relationship between the volume of water I physically got out and the volume of aquifer that experienced a drop in head, right? Okay. Now our specific storage is the volume of water so this is defined as the volume of water divided by the volume of head drop. All right, so this is my storativity. also normalized by the aquifer thickness. So B here is my aquifer thickness. All right, so this is volume of water volume of head drop and times aquifer thickness. All right, let's think about units here for both of these. Storativity is a volume over a volume. So this is length cubed over length cubed. All right, so this is unitless. All right, this one, specific storage, all right, these two cancel out, and so specific storage has units of 1 over meter. All right, and we can think about this as this, it's just, we can do some rearranging here, the specific storage. I can insert my definition for storativity here, S times B, all right, or sorry, S divided by B. It's a mistake, I'm sorry. All right, and this gives us S is equal to SS times B. All right, so for a confined aquifer, my storativity is this equal to SS times B. All right. For my unconfined aquifer, where I'm draining pore space, my storativity is equal to SY plus SS times B. Where SY is the specific yield, and it is defined by the volume of water released over the volume of aquifer gravity drained. So this is V water released, and this is the aquifer gravity drained. All right, so if I take a column of aquifer, and this is this aquifer has a water table. Right? If I drop that water table, right, delta H, then by extracting some amount of water VW. And again, here, says area A, then the volume drained is A times delta H. All right, and the volume of water is what I extracted. So it's the relationship here between the volume of water that I drained, or the volume of aquifer that I drained, and the amount of water I released. All right, so that kind of makes more intuitive sense in an unconfined aquifer because we're physically draining pore space. The specific yield is the dominant source of storage, and it's just how much water we release from draining. The specific storage for a confined aquifer for an aquifer that's with vertical deformation only. I don't know what that other line down there is. SS is equal to rho water G alpha times N beta water. All right, where alpha is my porous media compressibility. And beta is my water compressibility. All right, so specific storage is related to the amount of aquifer expansion or compression and water expansion or compression. Okay, so we started off thinking about porous media and an REV of porous media. And we went through and talked about how we measure things like the volume of water in it, the mass of water in it, the total energy of the water, or the potential, how we measure discharge and flux through porous media, how that discharge and flux is related to total energy or head via Darcy's law. And then finally, we talked about storage, which is a relationship between changes in head or energy and the volume of water in the porous media. All right, this was a rapid fire, quick review of porous media properties. It assumes that you've had some groundwater course before, and was designed to get you to start thinking about and remember how porous media properties work. Thanks for your time, and we will see you in class. Bye.